Okay, so in the previous class, we learned about how to handle procedures in a RISC-V processors. So please remember that in order to handle procedure jump, so which is the procedure code. Okay, so calling some procedures, which means the PC, the program counter, we change it to the first line, the first instruction of the procedure. So we need to use the jump and link. So also, why do we use link? Because when we jump to a procedure, then we need to remember the processor or a program. A program needs to remember where to return. Okay, so after the function call, the program needs to return to the very next instruction of the function call, right? So after the jump and link, then this jump and link stores the return point to the destination register. So also I explained that usually there is just a recommendation. So it means that this register number can be changed, but usually, the return address is stored in the X1. Return address is called the RA. Also, when a program returns from a procedure, and we need to use the return statement in C, and the return statement is translated into JALR. So actually, the X1 has the return address. So JALR is the return address from X1, usually X1, but actually the JALR can be return address from any register, but I mentioned that the return address is usually stored in X1. So JALR return address from X1, then so we can a program can return to the very next instruction of the function call or procedure call. So we covered some examples of a function call, like the lit procedures or non-lit procedures. So actually in the previous class, we handled the non-lit procedure example. So as I explained, this function is the recursive function. So which means that this function calls its own function, okay? So I intensively explained how these instructions are executed in a processor. So I hope you can understand how these stack pointers are managed and how the return addresses are stored, and then return addresses are used for returning from a procedure code. Okay, so actually this is the very good example for the recursive function, right? Okay, so also we briefly handle the memory layout, and a binary file is executed. So I said that this is the virtual memory, actually. It's a virtual memory. But we will learn about the virtual memory in chapter 5. So you may not understand what virtual memory is. But in a computer system, virtual means actually it's fake. Okay, it's not real. It's not real memory, but a program thinks that, oh, I can use this amount of memory in a computer system. The computer actually the virtual memory is managed by operating system, okay, OS. So actually OS assigns the virtual memory space to the binary file, so binary execution file. when the binary file is executed. So actually these addresses are virtual memory address, but we will learn about the virtual memory in chapter 5. So don't think that, oh, this is the address. So when a program is executed, then some memory space is reserved for some reserved area, but actually this space is reserved for kernel code. Okay, so actually the programs cannot access this reserved space. And then if a program is executed, then program has the instructions. Also, a program has many data, many constant data, or many static data. So it is, so instructions are stored into some space of the virtual memory, and then also the static memory, static data or constant data are stored in the static data area. And then after that, the dynamic data is allocated to the after the static data. Okay, so we can use this dynamic data using malloc function in C, or new function new in Java. Okay, or malloc. So as I mentioned, in this course, we frequently handle compiler-based language, not interpreter language like Python. Python is the interpreter language, so it's different from the compiled languages. So when a compiled language is compiled, and binary files are generated, and then these generated binary files are executed on a computer system. But in the interpreter language, each line, each state of the interpreter language is executed step by step. So usually the performance of interpreter language is much lower than the performance of C or C++, like the compiled languages. Okay, so we also learned about some influences of the compiler in this class. Also, if we see that this procedural code, then I also mentioned stack. Stack is the temporary space for storing temporary data in main memory. So this is the main memory. So if I said this is the virtual memory, but you can think that this is the main memory, the main memory space. Okay. So when a function code, when a function is called, then this function is to store some data in the temporary space, and then this temporary space is called stack. Okay. So if we see the memory layout, the dynamic data increases in instruction, okay, and then stack increases in row direction. Okay. So sometimes stack pointer can hit the dynamic data pointer, so it's stack overflow, but actually the virtual memory size is very large. So actually this case does not happen usually. Okay, so this is the memory layout. Also, I also explain about some another pointer, frame pointer. Actually, frame pointer is also used for managing stack space. Okay, so if you see this figure, so you can find that the frame pointer FP is here, and then stack pointer is here. So you know the stack pointer increases in this direction. So that's why we use add I minus immediate for managing stack pointer, usually when a function is called. But if you see this figure, so you can find that many temporary data can be stored in the stack space, like this is another saved registers. Okay, and then saved return addresses, also the local array. So it is also possible that local function may have very large array. Okay, and then so when a function is called, this local array data is declared inside of a function. So which means that this data is not used by main function or parent function. So which means that this local data array or local data is just a temporary data. So sometimes if the function size is so large, so which means the function handles large local data, then we need to store this local data in a temporary space, like a stack. Okay. So local arrays and some data can be also stored in the stack. So which means that stack size can be very large. So actually, in the previous example, the stack size is just a kind of just very small, like 8 or 12. But if, if the local function handles a large data structure, and stack size can be very large. So some compilers, some compilers, so actually compilers know how the stack is managed, because the stack is actually managed by compiler. Okay, so as you know, so we can change the stack pointer with some instructions. Actually, these instructions like this add I or store. So because this store access stack spaces. So these instructions are generated or managed by compiler. Okay, so which means the compiler already knows how the stack space is allocated by some, assigned to some data or assigned to some temporary data, something like that. But for some convenience management, the compiler can use frame pointer, and then usually the frame pointer is pointing the first memory space of the stack. Okay, so but it's optional. It's optional. Okay, so some compilers can use frame pointer like this. Okay, and then so now I will cover some additional instructions for the additional RISC-V instructions. So until now, so we learned about the arithmetic instruction or logical instruction. So which means the R-type instruction. Okay, what is the R-type instructions? So you can think like add x1, x2, x3. This is the R-type instruction, right? So R-type instruction is operands from registers, right? And then we also learned about the I-type instruction. So I-type instruction like MI, so like x1, x2, and immediate. So I-type instruction use immediate data, right? Like add. So we also learned about the arithmetic or logical instructions of the I-type instruction. And then another type of instructions is memory instruction. Memory, like load word or store word. So actually there are two kinds of memory instructions in RISC-V, load and store. It's a fundamental memory instructions. So in a load instruction, the load instruction read data from the main memory and then store the read data to the registers. And then store instruction. In the store instruction, the direction is opposite. So the store instruction reads data from registers, and then the read data is transferred to the main memory. And then we learned about the branch instruction. It's a conditional branch like BQ, x1, x2, like this. Also, we learned about the jump instruction. Okay, it's unconditional jump or unconditional branch in order to support function code. So this time I will also cover some miscellaneous instructions. Okay. The first instruction is the LUI. So we already learned that with the immediate type instruction, like the I type instruction, we can use small size constant data. Like, so I explained that we use this statement like I equal I plus 1 or I equal I minus 1. So which means that we use small constant operands very frequently. So in order to support this frequently use constant value, so RISC-V has the immediate instruction types. Okay. So and then also we also learned about some structure of RISC-V instructions. So we already know that the size of the immediate field is the 12 bit. Okay. And then it's the signed number. Okay. So which means that we can calculate the size of this immediate number easily. So it's a minus 2 to 11 to 2 to 11 minus 1. Okay. But sometimes they require very large constant number. So which means that the size of this constant number can exceed the size of this immediate field, such as we can have the very large number, such as the 4096. Suppose that 4096, and then the size of this it's large. It should be large. 8192. The size of this number is very large, so it cannot be stored in the immediate field. Then how can we handle this large number? So sometimes, okay, we frequently handle very small constant number, and it's true. But sometimes we require very large constant number. So then this large number can be also stored in the memory. Okay, so it can be stored in the memory, and then it can be transferred to the memory to the register file, and then so we can also handle it's a large number. But so you need to remember that the register file is very fast, so we can access register file very quickly. But the memory access requires large amount of cycles. So which means that my memory is very, very slow. So which means if we access data from the main memory, then the performance of our program will be degraded. So RISC-V also supports some instructions that can store they can handle large constant data. So like LUI. So the format of the LUI is the LUI, this is the destination register, and then constant. So as you can see, the LUI has only one destination register and then the large constant number. And then this is the definition of the LUI. So actually LUI stores this large constant number in the upper 20 bits of the register. Like it's 31 to 12. Okay. Then this lower part is filled with the zeros. Okay. Then how can you fill this lower part? Sometimes we may. So if this low part is filled with all zeros, then which means that it's like the multiplied by 2 to 12. So it's a very large number, but we cannot handle this low part. Then how can we fill this low part? So we can fill this low part with the add I. It's like 12. So we already know that add I can handle the 12-bit immediate number. So with this add I, and we can fill the lower 12 part of the destination register of LUI. So so which means that using two instructions, like first LUI and add I, then we can store 32-bit constant number in registers without accessing main memory, right? So this is the some it's not kind of special, but it's some uh, uh, special. Yeah, it can be called special. It's a special instruction that can that is used for handling large constant number. Okay. Okay, and then let's learn about the address of the branch instructions. So if you see the I will show this here. Okay. So if you see that this RISC-V instruction keyboard, then you can find that this is the format of instruction. But if you see the format of the branch instruction, you can find that the format of the branch instruction is the SP type. But if we see the branch instruction, then branch instruction requires the two source registers and then one immediate operand, right? And so which means that if the format of the branch instruction is similar to the actually store instruction. So if we see the store instruction requires the two source registers and one immediate operand. But RS1 and RS2 location is different, right? But branch instruction also requires the two source registers and one immediate operand, but the format of the branch instruction is SP type, not S type. Why? Because the addressing is different. So let's see what is different. So if we see the SB format, then this is the SB format of the RISC-V instruction. So as you can see, OP code is here. It's the same to the other instructions, like OP code is the 6 down to 0. And then RS1 is here, RS2 is here. It's also same to other instructions, also other SB S-type instructions. And then function 3 field is here. It's also the same. What is different? Even though branch instructions use immediate field, the immediate field is allocated differently. It's somewhat weird, right? The immediate 12-bit is here, immediate 10 to 5, 10 down to 5 is here, immediate 4 down to 1 is here, and immediate 11 is here. Why? It's different. It's different from other immediate type instructions like load or store instruction. And the store instruction is a store instruction. So RS2 is here, RS1 is here, function 3 is here, OP code is here, and immediate field is immediate 11 down to maybe here. I don't know this. Yes, 4 down to 0, then it's 11 down to 5, right? Right. So this is the S type. But if we see the SP type is used by branch instruction. The immediate field is weirdly allocated in the instructions. Why? So if we see the store instruction like the store word and RS2, RS1 immediate, then we can calculate the address of the store instruction like the RS1 plus immediate operand, immediate data, right? And then, we already know that this address is the byte address, right? So which means that the one in immediate operand assigned 1 byte data. So which means that 1 in immediate is the 1 byte, right? Because so RISC-V is used the byte address, and then most processors use byte address. Okay. So 1 in immediate represents the 1 byte. But how about the branch instruction? So think like this. So what is the program counter? Actually, the branch instruction, when the branch instruction is executed, then branch instruction changes the program counter of a program, right? So that's the destination of the branch instruction is the program counter, not register or memory. So branch instruction change the program counter. But I already explained that when an instruction is executed like add, sub, and more, then if this program counter of add is the PC, then program counter of sub is the PC plus 4. And which means that the program counter of the multiply is the PC plus 8. So what does that mean? The PC is increased by 4 in this example, right? It is because the size of a single RISC-V instruction is 4 bytes. It's a 32-bit, right? So which means that we don't need to use the RISC-V, the lower 2-bit, to represent the program count of the RISC-V instruction, because the RISC-V has the multiple with PC of the RISC-V is the multiple of 4, right? But if you see this format, then you can find that the immediate field starts with the immediate 12, and then it ends with the immediate 1. And then also, if you see this PC relative addressing, you can find that the target address is the current PC, the PC of the branch instruction, plus immediate multiplied by 2. Okay, multiply by 2. It's weird, right? So I mentioned that the size of the RISC-V is the 4 byte. So which means that the PC, the program count of the RISC-V instructions, is the multiple of 4. But it used the multiple of 2. Why? So it is because RISC-V also supports the 16-bit instruction. Okay, 16-bit is the 2 byte, right? It's a 16-bit. So RISC-V has the reduced size instruction. It's like a 16-bit. It's also same to ARM. So ARM, the size of the ARM instruction is also 32-bit, it's a 4 byte. But ARM also supports the small size instruction, such as thumb. So the thumb instructions, the size of some instruction is the 16-bit, the 2 byte. So actually, the branch instruction change the program counter. So RISC-V needs to have the PC, which is the multiple of 2. Okay, in order to support this reduced size instructions. Okay, like 16-bit instruction. So usually the instruction size is 32-bit, but sometimes the RISC-V can support the reduced size instructions, okay, 16-bit instruction. So in order to support these instructions, the program counter, actually branch instruction, the immediate, when the immediate field is stored in this branch instruction, then we need to calculate the target of the branch instruction like the PC plus immediate multiplied by 2. Okay, that's the PC relative address. So if you see the this table, then you can find that if you see that this BQ is here, the immediate field is here. Then if you see the definition of the BQ, then you can find that if RS1 is equal to RS2, then PC, the target PC of the branch instruction, is the current PC plus immediate. But as you can see, immediate is the multiplied by 2. So which means that it's the only 0 is added in the RISC-V of the immediate field, and immediate field is shifted by left. Okay. So like here, so that's why the immediate high format is used the SD format, and then SD format is different from the other X format. Okay, so it's a enough to support the multiple of 2 of the immediate value. Okay, it's the branch addressing, and then jump is also a little bit different. So you know, when the jump instruction like jump and link is executed, jump and link has the one RD and then the target of this jump instruction. So you know, when the jump instruction is executed, then jump has the one RD like here. Is RD is used for storing the return address. The object code is here, and you know, the immediate field is allocated the remaining. Sorry about that. The immediate immediate field is stored allocated to the remaining field of the instruction like this. Okay, it's somewhat different. Okay, so if you see the jump, there is jump here. So it's a jump and link is here, and the is here. And it's also, you can find that the immediate is the multiple of 2. Okay. So, and then its immediate is assigned to the instruction field like this. Okay, it's a little bit different. Jump and, but this is the UJ format. But jump and link register is different because the jump and link register has the RS1. So this is the I-type instruction actually, right? So the definition of the jump and link is like this. Okay. So this slide summarizes the RISC-V addressing mode. So which means that how the addresses or operands are calculated in RISC-V instructions. So the first type is the immediate addressing. So which means that immediate type instruction like I-type instruction. The I-type arithmetic or logical instructions can directly use the immediate data from the instruction field. Okay, and then for the register address means that it's the R-type instructions. The R-type arithmetic or logical instructions use the operand stored in the registers and source registers. Okay, so these data in source registers are directly used by these instructions. And then this is the memory memory type address. Right? So like the load word RS, RD, RS1, and immediate. So in order to calculate the address to memory, main memory, then the immediate field is added to the data in source register. Okay, so the which means that the target address is generated as a calculated, and then with this target address, the main memory is accessed. So another type of addressing is the PC relative addressing. So which means instead of register, then this type of instruction use the program counter as the base address. Okay. So with this PC type address, then with this new PC also the memory is accessed because the instructions are also stored in the memory. Okay. These are four types of RISC-V address. So we learned about some types of RISC-V instructions. Okay. And then I also covered some special instructions for handling large constant value. Also, I explained about the addressing of the branch instruction, or so addressing of other RISC-V instructions. So this is the end of the RISC-V instructions actually, and then so we will learn how the programs are translated and how programs are executed in a computer system. So until this part, we learned about the RISC-V instructions, like the RISC-V assembly instructions. Okay, and then these instructions are actually summarized in the RISC-V instruction set architecture manual. Also, in order to understand some instructions, RISC-V baseline instructions, then you can also see this summarized RISC-V instruction table. Okay, here. Then this time, so I will explain how the high-level language codes are translated, so it's compiled, and then how the compiled codes are executed in computer system. Okay. So this slide shows how the high-level program code are compiled. So the first, this is the C program. So as I mentioned, the high-level language code. So C program is just a text file. Okay, it's like other usual text file. Is our program. Our program just stores the text code like print add, main, and A equals 1, something like that. It's just a text file. So, and in order to execute this program, then this text file needs to be compiled. And then for this compilation, we use compiler. Okay. So as you can see, you can find the compiler here. Then compiler first generate the assembly language program, assembly code. So like we can write the code like A equal A plus 1. Okay. And then this code, it's just a text file. This text code is compiled with the compiler like GCC, the C compiler working in Linux operating system. So if we compile this text file using the compiler, then assembly code is generated. Okay, so like that is instruction, this code statement is translated like the add I, x1, x1, and 1. Okay, so high-level language code is firstly translated into the assembly code. And then using the assembler, then this assembly instructions are translated into the machine code using the assembler. Okay, and then this machine code is generated, then this generated machine code is called the object file. Okay, object file. So if you are familiar with the GCC or Linux operating system, then usually if you write the code with the C, then you can generate the code. The extension of this C code is the .c, right? And then if you compile the .c file using GCC compiler, then first actually the GCC compiler generates the obj file. It's the object file. So actually, if we does not specify any option like -s, then GCC compiler does not generate assembly code. Okay, so usually the compilers generate object file from our program code. Okay, high-level program code. Then our program code can use some functions like printf, Okay, then how can you use this printf function? We do not write printf function in our code, right? We do not write the code for the printf. So we can use printf if we include the standard IO.h, the standard IO library. Okay, what is the library? So library has the compiled functions. Okay, actually, this printf function is defined in standard IO library. Okay, standard IO.h. So if we do not declare the include the standard IO.h, then we cannot use this printf function. So which means that when we write the code, we frequently use some functions from many libraries, and then which means that when we generate the final binary file, these functions need to be included in the binary file. Why? We already learned about the functions or procedures, and then when the function is called, then the program jumps to the instructions in a function, which seems the printf function. And the printf function is called. It's a very simple function, right? The printf function is called. Our program jumps the first instruction of the printf function, right? So which means the object file from other libraries need to be included also. So in order to use the printf function, then we need to include the standard IO library. And then which means these functions, these libraries are also need to be merged in our program. So actually, this library has the compiled object file, also another object file. Then we need to merge these object files to generate the one binary file. Okay, and then this process is called linking. And then this process is also done by compiler, and then this function is called the linker. Okay, so linking means that when the function is called from other libraries, then object file of these libraries are merged in our program. It is called the linking. And then finally, the executable binary file is generated. Okay, so if we compile the program, our C code with the GCC, then we can default executable binary file name is the a.out. Okay, so this is the binary file. Then we can execute this binary file by executing a.out in our CLI, the command line interface. Okay, then if we execute this binary file, the binary file is also includes some instructions, and then I also said that instructions are also data. Okay, and then data is stored in the main memory. So which means that a.out is not just a file. The file is also a bunch of data. And then when we execute this a.out, the output of the compiler, then this a.out is loaded to the main memory. Okay, it is done by operating system. Okay, so a.out is loaded in the main memory, and then the computer, the CPU can read the instructions from the memory, and then computers can execute the instruction. That's how our high-level language code is compiled, and then executable binary file is generated, and then how this binary file is executed in a computer system. So compiler, assembler, linker is these are the part of a compiler. Okay, then compiler generates the binary executable file. Then using the loader, this is the kind of part of the operating system, and the executable binary file is loaded to the main memory. That's how our programs are compiled and executed by a computer system. Okay. So as I mentioned, compiler translates the program into the machine code or machine instruction. And then actually our binary file includes these information. So I will not explain about these information here. So this is the kind of operating system area. But as you can see, our binary file can include some information for executing our translated machine code. Okay. And then also I explain about the linking. So linking means that we can use the many functions from other libraries, and then it means that the machine code, the object file of these functions need to be merged into our binary file. So this is the linking operation done by compiler. And then that's how the programs are loaded into the main memory. Okay? So actually, this slide also mentioned the virtual address here, but we need to learn about the virtual address in chapter 5. So just to read this slide, then, but in order to understand the virtual address or virtual memory space, then you need to learn the virtual address from virtual address or virtual memory space in the chapter 5. Okay, just to read and how the programs are executed in the computer system. Okay. So then let's see why compiler options are also important for the performance of our programs. Okay, so this graph shows the performance of sorting and the compiled using some various compiler options. So if we use the GCC, okay, GCC is the C compiler, then we can also set the compilation option, compilation optimization options. Like minus large O, then we can define the some optimization efforts by compilers, like minus O1, minus O2, or minus O3. And then also we can apply the no optimization option, and our program code is compiled. So what does that mean? With the various compilation option like minus G, minus O1, minus O2, minus O3, it's the same program like the sort.c. Even though this same program is compiled, compiler can generate the many different binaries, okay, using the different compilation options, okay. So O3 is the most optimized binary. So which means that compilers try to apply the very high level optimization techniques. Okay, this is the O3 option. So from the same program code, we can generate different kinds of binary files, like compiled using minus G or compiled using minus O3. So let's see the performance. So the first graph shows the relative performance. So which means that we assume that the performance of the no optimization option as the 1. Okay, this is the relative performance. And then we just compare the performance of other optimization, like O1, O2, O3. As you can see, the performance is improved by like 2.413. Okay, right. So what does that mean? If we apply different optimization options, then the performance of compiled program can be improved. Like, as you can see, the performance is improved by 2.3 or 2.44 times. Right, it's amazing. Then what is changing? Let's see the instruction count. If we see, so in the chapter 1, so what is the execution time? Execution time is the instruction count, CPI, and clock cycles, clock period. So, and then in this example, the computer hardware is the same, so which means that the PC, the clock period is the same. We just apply the different compilation option. Okay, so compilers can change instruction count and CPI. So that which means that we can compare the instruction count and then CPI of the compiled programs. Okay, so if we see the instruction count, then as you can see, the IC, the instruction count of the no optimization option is much larger than the other optimized code like O1, O2, O3. That's why the performance is improved by compiler optimization. The clock cycle is actually it's proportional to the instruction count, right? No. The clock cycle is the proportional to the execution time, right? It's just clock cycle because the TC is the same. Then we can compare the CPI. If we just compare the CPI, then we can find that the CPI is higher when we use the O1 option. So execution time is the instruction count multiplied by CPI multiplied by TC. Okay. But if the CPI is high, then we can think that CPI is high. So it's not good for the performance because the execution time can be increased. But even though the CPI is increased, we can find that total instruction count is decreased. right? So that's why. So when we compare the performance of the program, then we need to consider these three factors: instruction count, CPI, and clock theory. So with the compiler optimization, then we can decrease the number of instruction count, but the CPI is increased. What does that mean? Compilers try to use complex instructions. Okay, so which means that clock per instruction may be increased because the more complex the instructions are used, but using these by using complex instructions, compilers can also reduce the instruction count. So that's why compile with the optimization level, we can increase the performance of the binary file. So it's amazing, right? With the different compilation effort, then we can also improve the performance of our program. That's why the compilers are also very critical for the performance of the computer systems, right? It's amazing. Also, program languages or algorithms are also very important. So this slide shows the performance of the bubble sort is the normal sort, and then quick sort. So as you can see, quick sort may be faster than the bubble sort, and then also, this bar graph represents the relative performance. So which means there is a relative performance, and then compiled using C compiler, which means that the bubble sort algorithm is written in C, and then this is the optimization option. So no optimization O1, O2, O3. Also, we can write the same algorithm with the Java. Java is also compiled language. And then you can see. And then also, but the Java has the two different modes. So which means that the Java is compiled. Java generates the Java instructions, and then these instructions can be executed on the Java virtual machine, JVM. Also, when we compile the Java, then we can compile our Java code using the just-in-time compiler. Okay, so instead of using Java virtual machine, then just-in-time compiler is directly executed on a native computer system. So if you see the relative performance for the bubble sort, then so we already know that with the more higher optimization level, then we can increase the performance of our C code. But if we just see the performance of Java, then the performance is also very, very low. So it is because, as I mentioned, actually, when we write the code in Java, then Java generates the Java instructions, and then actually the Java binary is executed on the Java virtual machine. So which means that Java instructions are interpreted on a Java virtual machine, and the Java instructions are executed. So performance, it's very, very low compared to the C code, right? But if we use the just-in-time compiler, the performance can be improved. Okay. And then this is the quick sort, which means that the algorithm is changed. It's the same sorting algorithm, but algorithm is changing. We can apply the quick sort algorithm. So which means that we can, if we just apply the quick sort algorithm, then we can also find that the effect of the optimization, compiler optimization are also changing. Okay, so we can also compare the performance of the Java Actually, if we use the Java, then for the quick sort, the performance of the Java is much lower than the C. So that means that program language also influence the performance of a control system, and usually the C exhibit the high performance compared to other program languages. Okay, because the C is kind of, but usually the other languages are high level languages, but C is just lower than these high level languages, which means that these can be can directly actually the C has the pointer. So C is using the C, and the C can directly manage some computer resources. Okay, so the level of the C is actually lower than the other high level languages. That's why the C is faster than other languages. Okay. So, and then we can also compare the performance of quicksort versus bubble sort. So, which is the relative performance of the quicksort compared to the bubble sort. The quicksort versus bubble sort to speed up. So, by changing the algorithm, it's obvious, right? By changing the algorithm, we can increase the performance of the sorting dramatically, right? So, the performance is improved by 2,500 times. Okay. So, thanks. Why did I explain here? Algorithm also very important. Actually, the algorithm decides the overall performance. So, if the algorithm is the same, which means that our code is the same, then we can also apply more a better compiler optimization techniques, so we can improve the performance of our computer system, like hardware. So we can increase the PC, we can reduce the PC, the clock period, using the better hardware. But algorithms may dominate the performance of our application. So that's why the good algorithm is very critical for the performance of our computer system. Okay. But if the algorithm is the same, the performance is also determined by compiler and computer system, the hardware of the computer system. Okay, that's also very important. Okay, then let's see the array versus pointer. So, what is array? So, array means that it can represent some multiple elements with the array, like A0, and A1, and A2. But you can also access the elements of this array using pointer. The pointer is the C operator. So then let's see how the array pointer can change the instruction, the compiled instructions in this file. So this program shows the array code, array version of the clear function. So as you can see, this function is very simple. So this clear one function is the two arguments is the array size and the array, and then so actually using the iterate for loop, and the elements of each element in this array is initialized. It is 0. Then if this program is directly compiled, then this is the compiled code. Okay. You can read this compiled code. But if we see the array code, this is the same function written using arrays. So if you see that this clear2 function, the clear2 function receives the array as an argument, so the size is the same. So as you can see, the P is declared as the pointer of the C. And then, P, and then by incrementing the pointer P by 1, and then we actually dismiss the data pointed by P, okay? So which means the data pointed by P. Then we initialize the data pointed by P. And then actually some students post the question of the piazza, and then this student as the Y. When the pointer is increased, then the pointer is increased by 1. So actually, I frequently use the AND operator to represent the address, but in a RISC-V assembly, then address used to be RISC-V used the byte address, right? So which means that when we calculate the address of some element in an array, then we need to calculate this address like the base address plus I multiplied by 4, because this number is determined by the size of data accessed by load instruction or store instruction. Store word, store help word, or store byte. But pointer is a little bit different. The pointer is the C operator. So when the pointer is declared, the size is also declared, right? So which means that if this pointer P is declared in C, it is declared as the pointer of integer type. Okay. So which means that when the pointer is increased by 1, which is equivalent to the, if you like, the address of array plus size of integer multiplied by I. You understand? This is because pointer P is declared using integer pointer. Okay, so which means that even though the pointer is increased by 1, which is equivalent that the pointer, the address is increased by size of integer multiplied by I. Okay, so it's a little bit different. So when the pointer is used and then this function is directly compiled, so this is the compiled code. So what is different? So which one is better? So actually the function is the same. So it initialize the element in array as 0. But if this is the array code, then the right side code is the pointer code, and then it is, and these are the compiled instruction, RISC-V instruction. Which is better? The better means the which exceeds the higher performance. Right, pointer is better. Pointer version is better. Why? If let us assume that the size is 100. Okay. So what does that mean? If the size is 100, then when this code is executed, this loop part, iterative loop, will be repeated 100 times, right? So as you can see, you can find the branch instruction here, and then the target of the branch is here. So by comparing I with the size, then it returns the loop 1, label of this loop. And then if you see that this code, you can find that the branch instruction is here, the target of the loop 2 here. Where is the loop 2? It is here. So what does that mean? If the size is 100, then this code, the instruction count of this code is the 1 plus 1, 2, 3, 4, 5. 500 by multiplied by 100. So which means that this code will execute 501 instruction. But if we see that this code and then this part has the 3, this part is the 3 also. So when size is equal to 100, then instruction count of this code is the 3 plus 3 multiplied by 100. So which means that 303. Okay. So which means if we just compare the instruction count, so no, it's true that we need to also consider the CPI, but if the CPI is the same, then the performance is determined by only instruction count. But if you use this instruction count of the different versions, then instruction count is also the instruction count of the next version is the higher the instruction count of the pointer version. So which means that this code is better. Which means this code is good for the performance. Then, so which means that we need to run about the pointer and we need to use the pointer for improving the performance. But it's not true because usually the compiler applies some compiler optimization. So compiler also can change the code like this array code into this pointer code. So which means the compiler also calculate if the compiler can change some arranging of the array element, then compiler also applies some optimization. So do not worry about the pointers because compiler can also apply some optimization. Also, this when the optimization is applied, compiler can generate the code like this, the optimized code. Okay, even though we write the code in array, and compiler can also generate the code like this. So do not worry about the pointer, okay? Because the pointer is the nightmare of C program actually. Okay, so I will stop here. And so actually, I will conclude the chapter 2 of this course. Actually, so in the chapter 2, we learned about the 5 instructions and the instruction set architecture of the RISC-V. Okay, so then in the chapter 3, we will learn about the basic arithmetic unit. So you can find the x86 instructions in the slide, but I will skip this slide, but this is x86 is a very complex instruction, so I will skip this part. Okay. Okay. Thank you for your attention. I'm going to see you in the next class.